Morning, Gabriel. Can you hear me?
Good morning.
Morning, nice job on the exam.
Thanks.
Hi, good morning, Daniel.
Dr. Chrysler.
Hi, how are you? Good morning.
Hello.
Hello, can you hear me?
Yeah, I can now. My internet is not that great, so I'm not sharing the video, so I could.
Okay, no problem. Thanks for letting me know. So I think the homework, I think two things. I accidentally had it hidden, which I'm fixing now. And then I think it also had the wrong due date, so. All right, so that it should be now the correct due date on there, and you should be able to see it as well. All right, good morning, Kelvin. Can you hear me, Calvin?
Yeah, I can hear you.
Okay, cool. All right, 8 a.m. So, let's see. So, yeah, thank you for taking the exam last week. The scores were pretty good. So I graded them. I put your score in the Moodle on the grade in Moodle. And then also, hopefully you saw the email that I sent you, which has basically the detailed notes or more notes about whatever from each problem that you did. I wrote some notes about it. If you missed some points or something like that. So those are in your email. So hopefully you have seen those. I couldn't figure out, I think there is a way to attach those in Moodle, but it's not easy. Moodle is sometimes difficult to use. Okay, so hopefully you saw those. The scores were pretty good. So usually someone gets 100 on this one. We didn't quite get there on this time, but several people got really close. So I think the exam went pretty well. Yeah, the grades, there's so you have all of those, and yeah, if you have any questions about your grade, feel free to email me or set up a Zoom appointment and we can talk about it in more detail. If you liked your grade, good job. If you didn't like your grade, we can talk about that. We can come up with a plan on how to study differently or whatever. So just send me an email or stick around after class and I'll stop recording or we can go into another room or whatever, and we can talk more about the exam and your grade. All right, so does anyone have any questions about the exam?
Would the solutions be posted?
No, the solutions will not be posted. So if you have specific questions, that's another thing. We can set up a meeting and I can show you exactly how to do stuff, but I don't normally post exam solutions. But I'm happy to show you exactly how to do the solutions and what the exact answer is. I just don't post them. So that's yeah, that's just how I normally do it. So any other questions? Okay, I think the other thing is the average, it was like an 80. So that's what I usually want the average to be. So so overall, yeah, it was it came out okay. So we have one more midterm exam, and that will be in several weeks, and we will have a final exam during the final exam week as well. All right, so 2 more exams. The next one, and during this this next section, we are going to focus more on magnetostatics. So the first part, we looked at electrostatics, and now we will look more at magnetostatics. And then in the second half, so this exam, for the exam 2, and for the upcoming coursework that we're going to do, we will focus first on the magnetostatics, and then we will combine everything that we've learned into time varying electromagnetics. So we'll have like 2 homeworks on magnetostatics and then 2 homeworks on time varying fields. And then we will have the exam 2. When we get to the time varying fields, we will also, that's when I will introduce the generator project to you. So there's a project for this class. It's kind of, you could think of the project as being kind of like a laboratory for this class. So a lot of times in a lot of places, electromagnetics does have a laboratory component. Here at ISU, we don't have a laboratory component, so I added this project in, and you'll have a chance to work on this project, which is kind of like a one laboratory experiment. It's a little bit more self-guided than a typical lab, and you'll have a bit longer to complete it. But we'll talk about that. I'll introduce that in another week or 2 when we switch over into it's the chapter 6 in the book and magnetostatics. All right. I mentioned, if you're just joining, I mentioned the homework I think was accidentally hidden previously. I just unhid it, and I also so you can go onto Moodle and find it now. And then I will also share it here. Sorry. Okay. Can you see the homework? Okay. So this section, we're going to look at this Biot-Savart, some problems on the Biot-Savart law. And this is going to be very similar to Coulomb's law. Okay, so the Coulomb's law, right? We had the cookbook where we looked at the location of the charges. And in this section, we will also be looking at the Biot-Savart law, which is looking at charges that are moving, and then being able to calculate the magnetic field due to those charges. Okay. So All right. For some reason my PowerPoint is not opening this morning for the slides. It just keeps saying that it's verifying PowerPoint. So hopefully that ends soon. So there is also, thanks while we're waiting, there's also a cookbook for this. So let me go over to the Moodle page. And you can find the Biosavar cookbook. So when we go through these problems, we will use this cookbook. So if you have a second, I would go take a minute and see if you can find this cookbook on the Moodle page. It's up with the other cookbooks. So the first part, the Biosavar cookbook, as you can probably already see, right, this looks very similar to the Coulomb's Law cookbook. And as we do the problems, you'll find that it is, in fact, quite similar to Coulomb's Law in terms of how we set the problem up. The primary difference is that when we get to the end, right, we are going to perform a cross product. So we're going to use a cross product expression here at the end, rather than the dot product expression that we had used previously. So let's see here. All right, cool. My PowerPoint is open and ready. So I'm going to paste in problem. To the notes. All right, so the first problem on the homework is about it says a semi-infinite linear conductor extends from 0 to z equals infinity on the z-axis. And the current flows in the positive z direction. And so we want to find the magnetic field intensity on the xy plane, where z equals 0 at some radial distance r. So let's draw this. All right, so this is the conductor. It's on the z-axis, right? And the current is in the positive z direction. All right, so let's use the Coulomb's Law cookbook to determine what the solution for this is going to be. All right, so take a minute if you haven't and see if you can find that, download that cookbook. And then once you have it, let's see what we should do. So we've just drawn the figure, the diagram, so we know what's going on. So in the cookbook, this should be the step 1. And now let's move on and see if we can write some vectors from the origin to the source current location and the origin to the point location. All right, so on your piece of paper, see if you can write up some vectors from that origin to the source. Okay, so we'll do that for the source current and the source current. Right before we had source charges, now we have source currents, and before we had origins and points. And so in this case, we're going to have those same types of origin and points. So see if you can complete step 2 and step 3. All right. All right, so what coordinate system do you think we should use?
The Cartesian.
Yeah, Cartesian, that one will work. And then do you think that there's any chance it would be easier if we did it in a different coordinate system? Yeah, we could also do it in cylindrical, and actually both of them will work. I think I actually have solved it I've solved this problem in both ways. If we do it in cylindrical, I will say that we, yeah, I guess the answer, yeah, does not actually say. So which way would you all like to solve this, cylindrical or Cartesian? Well, since Cade said Cartesian, let's go with the Cartesian solution, and then when I post the solutions, you'll be able to see the cylindrical one as well if you're interested in using it. All right, so what would the vector be for RS from the origin to the source location? We're in Cartesian, so do we have anything in the X direction or the Y direction?
No, we don't. Both those would be 0.
Yeah. So these are 0. And then in the Z direction, that one should just be Z, right? So if we go from the origin right here at 0, 0, 0, right, to any point on this Z axis where the current is, right, we will have Z. All right, what about RP? So to some point, so the question says we should find the magnetic field at some radial distance R. So what will that radial distance be? What will that point be?
It'll be X in the X hat direction, Y in the Y hat direction, and 0 in the Z hat direction.
Yep, that's correct. And I think that, if I remember right, in this case, don't actually end up integrating, but I'm just going to write some YP and XP just to remember we don't integrate these ones. All right. Now let's go to step 4. All right, so what is RSP? And then while you're at it, also find the RSP hat in step 5. Let me know when you've got it. Did anyone else get this?
Yeah, I got that.
Okay, perfect. And then I think you guys are all old pros at these steps by now. Anyone else get this?
Yeah.
All right, great. So now let's go on. I think these steps, do you all feel comfortable and confident on these steps? What do you think? What's anything different? What do you think? Anything trickier than the Coulomb's law stuff so far?
So what exactly do you mean we don't integrate XP and XY?
Oh, when we we're gonna get to a part where we do an integral in a minute. And I just changed it to XP and XY to remind us that these points are constant and we aren't going, if we get a DX or a DY or a DZ, we actually won't be trying to integrate these ones.
Okay, I get that.
Yeah. So I just marked it. I don't think it actually comes up on this problem, but in the Biot-Savart ones, you can end up with some even trickier integrals because of this cross product. You can get some stuff that's pretty hard to solve. And so I just sometimes it's easy to get lost in your variables. So I added these XPs just to remind us. So in some of the future problems, it may actually end up being more helpful than this one. All right, so now we are at the next step. So let me go back and share the cookbook. So again, if you don't have this cookbook, or oops, haven't pulled it up yet, we've done step 1, 2, 3, 4, and 5, and so far these are very, very similar to the Coulomb's law steps. But now in step 6, we're going to get into the parts where this is a little different. And don't get stressed or anything. It's different, but it's not that much different. We're just going to be doing similar things to what we did in Coulomb's law, but instead of charges, we're going to be identifying currents. And I also, if you really love math, I do want to point out that this cookbook would not probably stand up to the seal of approval of your calculus teacher. There's a little bit of, these vectors are not all true vectors, but the final result is a true vector. I've written it this way so that you can follow the steps along and get to this I1 result or II result. Okay. So I'm not sure who did you all have for calculus? Who teaches that? Jungrong, maybe? Dr. Ju, is that? I don't know. Jessica? I don't know. I don't know who. Don't show her this. So yeah. Or I can't remember who all the other calculus teachers are, but these vectors might not stand up to their approval. Okay, so we need to determine now if we have a line current, a surface current, or a volume current. Which one do you think that we have in our problem?
Line current.
And how did you know, Mario?
Because we're just dealing with that line current that's going in the positive Z direction.
Yeah, I think, does it even say that it's a line current?
Believe it does.
Okay, yeah. So I think it says, yeah, it's a semi-infinite linear conductor. So from that linear word, we can probably deduce that it's a line current. And we also don't see any information about the current being on different parts of the surface, or it being on a surface or a volume. Those are all possible, but in this case, yeah, we just have a linear conductor, so we have a line current. All right, so we are in rectangular coordinates. So what should we come up with for our value of this vector II? What should our vector II be? So we're in rectangular, so we know it's going to be dx, dy, or dz. So which one of these should we select for our problem?
Easy.
Yeah, we should choose dz, and that's because that's what the current, right, is changing in that z direction. So we go here. If we move along this line, right, where our current is, when I move along this line and I go up, it is moving in the z direction. Z is changing. So we'll choose dz. So this II vector is some I dz, and the current is in the I direction. So for ours, or in the z direction. Right, it's in the z direction, and it has some current value I, magnet. So the magnitude of the current is I, and the direction, right, is here. All right, so going from here, right, this part is I, and this part is the DL. So this is the step 6. All right. So now in step 7, right, we should find the cross product of these. So we should find the cross product of the current that we just determined and also the vector that we wrote here. So we should choose the RSP vector. All right, so on your paper, set up this cross product. All right, so set up the cross product and solve this cross product. All right, so solve the cross product of these two vectors. And if you need any help or tips, there's the vector cookbook and the calculus cookbook, which may have some more helpful information for you if you need to go back and see anything. And then once you've got an answer, see if you can upload it to our shared drive. All right, I'm seeing one answer. Anyone else get anything?
Yeah, I just need to upload it.
Okay, cool. I'll give you another second. All right, so seeing this. All right, did anyone else get this result?
I got something similar.
Okay,
My X was negative.
okay. Yeah, let's see here. In the X direction, you had a negative result?
Yes.
Yeah, I believe that is also what I got. Now, I think too, there's one other thing, which is, so we have this vector, we have I cross with RSP. And so in this case, let's take a look at this. Is this result, if we have this vector 1 crossed with vector 2, should vector 1 be in the first line or the second line?
It should be in the first line.
Yeah, so this line should actually be vector 1. And this line should be vector 2. Okay, so let's take a look at another, see what else we have uploaded. All right, so this is another upload that we had. So let's see. On this one, we got vector 1, vector 2, and they're in 1 and 2. So I think this one may have had a couple small mistakes. So let's look at this one. We got vector 1 in the right place, vector 2 in the right place, and then also, right, the vector I, this whole vector does include, we have the magnitude I, and then also part of the magnitude, we should include this DZ term, okay? Now, so this DZ term should go in here, just like we see here. Okay, so I think, yeah, this is also quite close, but there's one other thing that I want to point out as well, which is that on this vector, this is RSP, and this will be a YP, and this will be YP, whereas we have the Z source, okay? So I'm going to change these to YP to denote that that is the point, not the actual source location. So all right. So this is the result that I got for it. And it looks like several of you got it, or we're very, very close on it. All right, so step 9, asks us to continue on and to find do the actual integral here. Okay. So we should set up, we found the result of that cross product, and now we should set up and solve these integrals. Okay. So these are the steps in that cookbook. And we have the way that we're doing it. Again, this one is a little bit more simple, but we're going to keep, right? We have XP, YP, and ZP. So it's important to keep these terms denoted later on because some of the integrals do get a little bit more tricky. So whatever your points are from, so when you're making this RP vector here, make sure that you follow through with keeping the P associated with those directional components. All right, so we just came up with this. So now we should be able to write this DH. All right, so we have the cross product that we just came up with minus X then XP YP Z squared. And then we had this as a square root. And the whole thing is going to be cubed. Okay, did anyone else get the same thing?
Yeah, I got that as well.
Okay, perfect. All right, so now we have this differential expression. And what do you think we should do to solve this? We have a lot of stuff here. What do you think our approach should be?
Well, we can split it up into the X hat and the Y hat, but then also pull out all of the constants.
Yep, yeah, totally. I think that is a really good start, right? So does everyone else, I think you probably all see this, but right, this term, right, this is an X hat term. And then we also have the Y hat term on the other side. So we can easily split these up into two different integrals that we do that have the same denominator. So I think that will be a good first step. What else should we do? Is there anything else you can think of we should take note of as we approach this integral? And you said too the constants, right? So let's go back. What else is constant in here? Let's take a look and note everything that's going to be constant in our expression. To start, I'll start it off. XP and YP, right? Those are constant. What else is constant in here?
Won't I be a constant?
Yeah, we don't, the I is not changing, right? This is not a time varying current. So we got this constant, this is. What about these? That's constant, right? 4 pi. So Z is what's changing, and it's in this square root house. And it's cubed. So I think the only other thing that we should know is that this is probably going to be a tricky integral, right? You're probably going to need to look this one up, maybe. I don't know. But it's maybe not. But it is, we have Z in both It's in the denominator, and it's you know, it looks a little intimidating. So let's, you know, see whether it is or not. So put it in here. So let's take all the advice that Calvin mentioned, and let's break this up into two different integrals. Okay. So the first one is in the x direction. Okay. And we have this, the constant terms, we'll have this minus ypi and 4 pi. And then on top, all right, and what should these z integration limits be? So we should go from the start of the current to the end of the current.
In the problem, it says 0 to infinity.
Yeah, so we should put 0 to infinity here. All right. All right, so now take a minute, see if you can write up this expression for the y hat part of this. So see if you can write up the integral for the y hat part. All right, anyone get a result? So what should the front part be? What should our constants be?
XP I over 4 pi.
All right, yeah, I think so. And then what should the integral be?
The same as the x part,
Yep.
x hat part, yeah.
Yeah, it's actually the same integral here. Missed that. All right, so it turns out, right, we only need to solve, it's one integral. It appears 2 times, so we only need to solve this one once this time. So Did anyone happen to solve this already? All right. It's a little bit tricky, and we all know how to do calculus, so I'm just going to paste in my solution for this. So this one, because we have that infinite limit and the zero limit, we do need to take some limits on these. But the limit as z approaches infinity is 1 for the solution, and as z approaches 0 is 0 on this solution. So you're welcome to go back and verify, but you end up with this as the result of the integration. And then you need to take this, right, and evaluate at 2 different points, infinity and z. And so really what we get, this whole integral, right, from right, the result of this is going to be 1 minus 0 on this part. Sorry. Okay. So this limit part. So we'll have 1 minus 0, and then a squared and the b squared, which in our case, we have, this would be a squared in that integral, and this would be b squared. Okay, I think I got this correct now. All right. Yeah. Okay, any questions? Move this so it looks like more like that. Okay. So the final result on this for our magnetic field. This is the magnetic field intensity. In the x-hat, we have YPI for 4 pi. All right, so now we have an expression for the magnetic field intensity based on that current. So does anyone have any questions? What's the most confusing part of this?
Integration.
Yeah, the integration can be pretty tricky. And to be honest, some of the ones we're going to see in the future are even more tricky than this. Okay, so when we get into this Biot-Savart law, we'll see some really tricky integrals. And some of the problems on this homework, I believe, even just say, like, we won't even attempt to solve them. So let me just bring up the homework. here, right? This question 3 is about a conducting sheet. And in this one, the final result, in fact, I'm just asking you for an integral expression. Okay, so the integral is tricky enough that we're just going to find an expression for it. And then same with this one, right? We're just going to set up but don't solve for an integral expression for the magnetic field. So some of these, like question 3 and 4, they are much more tricky. Question 1 and 2, we can solve these, we can complete these, but 3 and 4, they're quite difficult to solve. And so we're just actually going to get to the point where we have created an expression. We've come up with an expression that you could solve. And so I think you might remember I mentioned earlier in this class, but great people who work on these electromagnetic problems in the real world, they often they have computer programs that solve these equations, and that's what they rely on to come up with their results. So in the real world, there can be expressions, integral expressions that are too complicated for anyone to realistically solve. And so we, in this class, we solve them by hand to get an idea of what those integral expressions are, why it's difficult, and why you would want to have a computer to solve them, and also to create kind of a bridge between your calculus knowledge and the electromagnetics knowledge that we have. So yeah, great point, Daniel. These are tricky integrals, and on the exam, or the homeworks, I would give you information like this if I wanted you to actually solve it. Does that help you feel better about it?
Yeah.
Okay. Yeah. Okay. Any other questions, thoughts?
So this is we're talking about magnetic fields. So why doesn't this have some, I know in our electrical charges and stuff, we had the constant that E naught. Why doesn't it have some form of constant that goes along with it? Because it does have the 4 pi.
Yes. And if we, yeah. Why? Now I'm wondering, did I just forget that? Let me double check this. Yeah. That actually is a good point. Let me make sure that I didn't leave a typo in there. Something on this. No, this should be correct, and the reason is that that when we solve for the B field, that expression will appear in there. So yeah. So just like in the electrostatics, that's a great question, and I really should have known the answer straight off on this, but it's early, right? Okay, so we have this expression, this relationship, and this is similar to our relationship for the E field. So when we solve for H by itself, usually we don't have the mu in it. And then with the other ones, this epsilon appeared frequently because in the Gauss's law, due to the way that we solved it. So later on, we will see the mu when we solve for the flux density. So it's coming, and we'll look at it some more, but it's not in these H field expressions.
Okay, that makes sense.
Yeah. All right. Any other questions? So we didn't, in the videos, this should be explained more, but right, the magnetic fields too, they're governed by this. So what does this mean? The divergence of the flux density is 0. What does that mean? Let's take a step back. What did this mean? There's a source of charge right here. And if we look at the field, if we take the divergence of the field, we can find out if there's a source in a location. So if we have a field, right? And the field, the D field is due to charges, right? So if we have a if we have an E field, right, it's associated with a charge. And we could take the divergence, right? We could take the divergence of the field, and we could tell how much charge is there. So what does this one mean? No matter what, when we take the divergence of the B field, it's equal to 0. What does that mean? So I heard someone speaking, but I didn't quite hear anything. So this is associated with charged particles, right? What about if it's 0? What does that mean about the B field? Are there any particles associated with that B field?
That means there are no particles.
Yeah, there is no magnetic charge particle. Yeah. Okay, I think this is sort of, I don't know, if there's one reason like to take a calculus based or like a, once you learn Calc 3 and you go back, this is like one of the main things that I think is good knowledge to have, is to use this calculus knowledge to realize that the practical meaning of the divergence and understanding these fields is to see that the divergence tells us about sources and sinks of something. So if you have any field, right, if you're dealing with fluids, the divergence of a fluid velocity, right, the divergence of a fluid velocity will tell you the density of the fluid in that location, right? So you could find a source, a high density or a low density, a source or a sink in your fluid, right? If you have a compressible fluid, you could take the divergence of that fluid and find information about the density. If you're in electromagnetics, you can take the divergence of the E field and find this. But we have this physical knowledge about the magnetic field, magnetic flux density, that when you take the divergence of that field, it's always 0. It's like 0 density. That means there's nothing there, and there's no actual source of that field. And so the source of these fields, of the magnetic fields, is always associated with current. And that's where this other relationship comes from. And this J is a current field. This could be a surface current, volume current, or a line current. So that's the main thing. One of the main things that I think you should come away from this class understanding is that there's no magnetic charge particles, and we do all this calculus because to see that, and this is a pretty big point that influences the way that we have to solve all these other problems. Okay. Sorry, kind of just just wanted something to say about it. I usually don't try to lecture too much in here, but I think it's a good point. Any other questions about this, setting up this Biot-Savart law? Okay. All right. So if you need to now, step 10 is to go back and convert into cylindrical spherical coordinate system if necessary. Okay. So this is the step 10. And in this case, right, we may want to do this, right, because the problem itself asks us for the H field at a radial distance r. Okay. So if you need to, go back and substitute in your information and convert this into the cylindrical coordinates, right? So that we have our answer as a radial form. Right. So this is the conversion method. So take a minute and see if you can convert this. Okay. So see if you can convert this into a form that is a function of the radius. So instead of YP and XP, try to convert this into something that is in the form that's a function of RP. And then once you have a solution, to upload a screenshot of that to the shared drive. Right, so this, right, this looks like RP squared.
I'm just looking for the expression, right?
It's a what expression?
Are we just looking for the expression, or do you want us to like simplify it?
Yeah, you should have, so you should get something like R or H hat is in R, you know, you'll have R, phi, and Z. We already know it's not in the Z direction. So we need to check about the R hat and the phi hat direction. So for this example, right, AX would be RP sine phi I over 4 pi RP squared cosine phi plus oh, oops, and this is a negative. All right, so what is this equal to? All right, what is this plus this? Is it too small? Too early? Too early in the morning? What is this? Plus this. It's written a little weird, but it should be pretty.
Isn't that just 0?
Yep.
Wait,
Yeah.
yeah, 0, yeah.
Yeah. It's just 0. So R hat in the 0 direction. So now we just have a phi component that we need to find. And if you simplify that, you should be able to simplify that a little bit. And it turns out that the phi is it I over 4 pi RP. Okay. All right, and that is the final answer is in the radial with in a radial direction. So the last step, if you need to, convert back into coordinates that that you're interested in or that you're looking for. All right, I think that is about it for today. The next problem 2 is quite simple, or not simple, but similar. Sorry, it's very similar to this one, except for the integration limits are set. So when you get to the charge integration, you integrate from the start of a charge to the end of the charge. The other 2 problems are a little trickier, but there's videos that show you how to do them. And they are somewhat similar. They're both surface charges. I'm kind of, I have something on Thursday. I may need to cancel class on Thursday. And if I do that, I will, please watch the videos that are already up. And then I will also link to like previous year's videos when I lectured on this topic if I need to cancel the class. So keep look in the announcements. And if I do that, I'll probably change the homework due date to next Thursday, so that if there are any questions, we can cover them briefly at the beginning of class on Tuesday next week. So any questions about that?
No,
Give us all a little bit of a break from 8 a.m. Yeah, actually, I'm just gonna go ahead and do that. All right, so let's, yeah, because I'm not sure about this other thing, and so I'll just say it now. On Thursday, the class will be canceled. I'll link you to the other videos on these problems, and then also do watch the videos, because I know those problems, a couple of them are pretty similar with the setup, the integral, but do not solve, and they'll help you out. So okay, and then I'll update to the homework to be due next Thursday. So if you do have any questions, so try to see if I'm not planning to, so next Tuesday, I won't plan to spend very much time on this homework assignment, which is a little bit of a shorter one anyways, but I won't spend very much time on it. So if you have questions, bring them to class, and we'll spend like the first 20-30 minutes on Tuesday looking at any questions that you do have. But if you don't have questions, we'll just jump straight into the next homework. Yeah. Okay, all right, well, I'll see you all next week. If you have any questions about exams, the class, etc., stick around on this, and we can chat about it. All right, see ya.
So about the exam, will we get our work back at all? Like,
Oh, I can send you that. Yes, for some reason, I can send you your exam back, because yeah, they scanned it and sent it to me. So
okay, yeah, because I was like looking at the feedback you gave me, and I was trying to figure out what exactly I see where I could have gone wrong, but I'm not sure exactly how I worked through it that day.
Yeah.
So
okay, let me
thank you, I appreciate that.
send this to you before I forget.
If I can get mine too.
Yes, yeah. All right, just sent yours, Calvin, and then Daniel. Sent yours, should appear in a few moments. So.